Hi, Professor.
Hi, how are you?
I'm doing good. Yourself? Can I ask you, please, a question, if that's okay?
Yeah, go ahead.
I was just a little confused from last tutorial, or maybe it's me that misunderstood. Whenever we're doing sort of the um, distributive law, or I think it's anyways, those laws, the
Yeah.
answers that were provided were sort of like if we had A union um, let's say B intersection C,
Mm.
then we needed to show sort of a left side equation that is equal to a right side. But I don't recall that in class I mean, we saw where it comes from, but could we have not just provided the answer directly? Could we have not given, what is in brackets, B intersection C, and then just do the union with A? Do we need to do the whole um, line? I
Oh,
don't know if my question makes
thing is, if so, it depends what I'm asking. So, if I'm asking, show that this example follows the law, then what you do is you do the example and you show that yes, the law applies. But then, if I'm asking you, please prove something new, then of course you don't have to prove again what we just did in class. You can say, oh, by the theorem we've seen in the class or the claim we've seen in the class, then I can use this rule to apply to this proof. So of course it saves steps. Uh,
Okay, I see. But for example, in the assignment where you're just asking, A union something, like the question is just directly numbers, then we don't need to do all those steps, or do we?
okay, so that's tutorial number 1, right?
Yeah, it's tutorial number one, but essentially I'm asking it for like the assignment. And the assignment question one, we're asked A intersection B and A you know,
Oh
you
yeah. So if
so
I say given A 456, B 34567, C verify the distributive law, then what I'm telling you is please do it explicitly. So you start with B intersection C, so you find 3, 6, and then you do this union A, so 4, 5, 6, and then it gives you 3, 4, 5, 6. And then what you do is you say, okay, what if I did it the other way? So A union B intersect A union C. So you start to do union B, then A union C, and then you intersect both, and lo and behold, you get the same thing. So yeah, so uh, I showed you a explanation, graphical explanation in the class where this would come from, but
yes.
you cannot really say it's a super foolproof proof that would satisfy mathematicians. Mathematicians are not satisfied with just drawings. So it's still good to just verify that it applies in that case, for instance.
Okay, sounds good. That's clear. Thank you so much.
No problem. Hello, everyone. How is everybody doing? Good, hopefully.
Good, you?
Good. So we have lots to see today. So how about we start immediately? So I'll just give you back the question we had last time. Okay, let me share my screen. Okay, here we are. I'm just going to paste this. All right, so about how the class is going. So I was, it's the first time I'm giving it, but I'm trying to follow as much as possible what was done last year. So one thing I really wanted to give you is a lot of small quizzes online, as you've seen a couple of times. But these take a bit of time. I think they're very useful because it helps you understand one notion and then we can continue on with the rest. Thing is, and also I said it's mostly an applied class, but still it's math. So there are some proofs. So I wanted to prove as many statements as possible when I give you a statement. But I see that, yeah, it's so if I follow the tutorials, then we have many things to see over time. So yeah, so we don't have all that much time, especially today. We have many things to see. All right, so I probably won't have time to do all the proofs or give you all the small quizzes I wish I would give you, but at least you get to have the TA sessions to practice on them. By the way, how did it go last time? Good. Good. All right. Okay, so let's continue on. So we finish quickly this section, then we start the next chapter, which is fundamental. I would say the most important, probably the most important chapter. Okay, we were doing this multi-market partial equilibrium. So the only difference with the first one is here we have two demand equations. So, and each market has the demand that is a function of their own price and of the other market's price. And then we had just described what goods are these markets. Now I've given you the other, of course, the other side of the market, the supplies. So as we can see, there is something strange going on here. So Q supply 1 is a positive function of P1 and QS2 is function of P2, but QS2 is not function of P1. Whereas here it is. Somebody has an intuition for that?
Well, because it's the supplier we're talking about, they're willing to produce more if the price increases.
Yes, and so imagine it's so how did we say now we so yeah, okay, so we said good one is a substitute for good two. So then what this means is imagine that good one is, I don't know, Coca-Cola, and good two is oh yeah, so I said good one is tea and good two is coffee. And then what we're saying here is coffee supply doesn't depend on tea's price, which makes sense because the supply just depends on however it costs me to produce what I'm producing. So, and what income I can get. So my income is directly dependent on the price of my product, but it doesn't depend on the price of the other product. All right, so let's solve this quickly. So, oh yeah, by the way, so just counting the equations there, I've got 1, 2, 3, 4. What we would say, yeah, counting equation. So how many unknown? How many equations do I have? I've got 4. I would say behavior equation. Or that depend on the rationality of agents, that assume that agents are rational. Here we assume that this is the best choice that consumers can make to buy. So the quantity of good one, this is the best choice they can make to buy quantity of good two. This is the best choice for producers. Now, what do I need then? I need 2 other equations. I would say are market equilibrium equations. What are they?
QDI.
QDI
Is equal to QSI.
Yes. For I also 1 and 2. So I get 2 others. And how many unknowns do I have? I've got 2 prices and I got 4 2 prices, 4 quantities. So I've got 6 equations and 6 unknowns. So I should be good. Is a solution is the oh sorry, I'm going to close this. Am I guaranteed to have a solution? Yes, no, maybe. At least I have got the same number of equations as unknown. So that's a start. Sorry about that. Oh yeah, there's the discussion there. All right, I don't think about following that, but yeah, I should. Not exactly. You might find that QSI doesn't equal QDI. Yes, exactly. So I need a yeah, I need a unique solution. And that's what we're going to see is sometimes it happens, sometimes it doesn't happen. So let's go for it. So let's start with, yeah, so QD1 equals QS1. So I get this equals to this. So then I get minus 4p1 equals to 0, or I could put it this way. Wait a second. Yeah, no, this is fine. Yeah. And then I do the same for QD2. Right, and yeah, what I can do is just put P2 on the left side and the rest here. So I get 4P1. Here I get so let's divide by 4. It's funny, I don't get the same numbers as I was getting. Okay, I think I changed my number. Anyways, I can solve it for this one. Okay, so tell me if I'm making a mistake somewhere, but I think that then what I can do is (12p1 minus 2p2). Oh, did I make a mistake somewhere?
Oh, because we
12p1.
did equal QS2. Right. So
Yeah,
that's minus 4.
Q, yeah, so 12p1, 12 plus, yeah, it's fine, right? Okay, so then this is 8 half minus 1, so it's 7/2. So I can divide by 7. I multiply by 2. Yeah, I get one solution for P1. Then for P2, I can just substitute in here, for instance. So it's 4. Yeah. All right. And then, yeah, then we can find the other quantities. Oh, yes, let's save that. So it's 10, 0. All right, so that's what we get. So we do have one exact solution. So we get, yeah. What we could have found. So somebody knows what we could have gotten? One, I would say one unique solution. We have two other possibilities. Yeah, no solution or infinite solution. So no solution is when you get something like, so like a contradiction. You get something like 3 equals 4, for instance, or 1 equals 0. So then you know that you're trying to solve something that doesn't have a solution. And yeah, you get essentially parallel lines and infinite solutions. You get you get an infinite number of solutions because you have essentially one. So you have two equations that are redundant with each other. And what we're going to see is why this is the case. So in the next chapter, yeah. Or maybe I could show you graphically what this would look like, but did I already do that? Or not? Hmm. Yeah, I don't think I already did that. So let me show you briefly graphically what this looks like. So I'm going to show you in 2 dimensions, but you can the same could happen for any number of dimensions. So this is when you have one solution. and you find X and Y, for instance. Then when you have no solution, the two are exactly parallel. So you cannot get any number. So this would be essentially you're saying, I want to try to find a point that is common to both curves. So what you get is, well, if you want to find a point that is common to both curves, then you need to find that, for instance, 2 equals 4 equals 2, for instance. That's the only way, because of course you cannot find this, so that it means that you have a contradiction. And then lastly, infinite solution is when they are, of course, exactly the same. So let me put this in like this, so we know. All right, so that's what we get. And so for now, we don't exactly know how to do it other than trying to solve the system. And once you get to the end, you know, oh, do I run out of equations? Do I have a contradiction? Or do I get a nice solution with one unique solution for my system? But what we're going to see next is how to do this systematically. All right. Does that make sense? So maybe you're a bit sleepy this morning. I am too, don't worry. Okay, so going back here. I'm just alive beneath these caffeine eyes. Yeah, good one. All right. So chapter 4. Which I have entitled Linear Models and Matrix Algebra. Oh yeah, no, sorry. There's one last thing I wanted to do here. Yeah. Sorry. Let's go back to chapter 3. Because this was shown later in the book, but I thought it's useful to show it now. So notes about the summation operator. So I'm sure at least some of you may be familiar with this, some of you not. How many people have seen it? So you can just say yes in the chat. So then those who haven't seen it don't have to say anything. All right, lots of people. Okay, so yeah, is it useful for at least one of you to see it again, just to be sure? Yes, okay, all right. So let me just show it briefly. So why do we use this? Well, we use this because it's much simpler to write down and to express complex expressions simply. So for example, we're just going to see examples. So x1 plus x2 plus x3 plus x4 can be written as sum I equals 1 to 4 of xi. So this is how we write it. So here we say we have some iterator I, which is going to have the values, so have all values, so natural numbers, or yeah, it could be any integer actually, which start at the first one here, 1, and ends at 4, and which will, so we will substitute 1 to 4 here. So here it would be, since we have 4 numbers, so x1 to x4, so we just write it this way. All right, and if we didn't have this, if we had numbers, if we had, say, 1 plus 2 plus 3 plus 4, so that would be equal to simply sum of I, and it would, of course, be equal to 10, if I'm not mistaken. Yes. Now, some properties. If I have, and of course, I don't have to say what number it is. I could say it's going from 1 to n. And if I add together I from 1 to n of some other set of numbers there, then how can I add these two? So yeah. You make sure that the i's are the same. Yeah, so how, yeah, that the summation is over the same set of numbers. Here, what I'm saying is I should be from 1 to n here and from 1 to n here. And if you have this, then you can just write summation of xi plus yi this way. So this works because it's just a summation. So a summation, you can combine things. So the associativity rule, so you can associate them before or after. All right, if you have then multiplying with by a constant. So for instance, if I have a multiplying this, then it is equal to the sum of axi. So this is quite easy too. You just think, well, if I have x1, x2, x3, x4, then if I add them, it's the same as if I, add them together and then multiply the whole thing by a, of course. Yeah, useful for polynomials. So if I have something like summation, see now I started at 0, not at 1, of ai x exponent I. So what do I get? I get a0 x to the 0 plus a1 x1 plus a2 x2. And of course, x to the 0 is just 1. So I get a second order polynomial. So it's a very neat way of writing it. Very easy. It's useful for infinite sums. So if I have something like sum from I equals 1 to infinity of say 1/2 to the I. So then I can just, this is very neat. I just have to write it this way. And so of course it's equivalent to 1/2 plus 1/2 squared. So that's 1/4 plus 1/8. And what is the summation?
Infinity?
Not quite. So, okay, this is maybe a bit more advanced, but so to find out the value of a infinite sum, you find the limit of the partial sums. Partial sums means the sum up to this point. So partial sum would be yeah, one half, and then partial sum is 1/2 plus 1/4. What is it? Oh yeah, I've got the right answer there. So it's 3/4. Then plus 1/8, it's 7/8. And then it's, yeah, 15/16. And this is how you know whether your sum is diverging to infinity or not. It's possible, it's perfect if you have something like 1 plus 1 plus 1 plus 1, yes, this goes to infinity. But if we have 1/2 plus 1/4 plus 1/8, we see that this sums up to 1. Yeah, and we have, yeah, somebody has shown us the right value. So n minus 1 divided by n. No, I don't think that's exactly right. Yeah, it's 1 over 1 minus n. Okay, let me do it quickly. So how do I find out when I have, well, okay, no, we'll see that later. Okay, so now cousin of the summation operator, the product operator. So it's exactly the same. It's just that instead of adding together stuff, we multiply them. So 1 times x1 times x2 times x3 times x4 would be, oops, not this. Yeah. Would be written this way. And it's exactly the same. So what you do is you just multiply all of them together, and this is the same thing as expressing it this way. By the way, if I take useful property, if I take the log of this, what do I get? In terms of sum, Yeah, I get sum of logs. Yeah, so I get so this is useful in econometrics. But we're not there yet, don't worry. Yeah, so I can, so I'll go back to this. So somebody has suggested, so to do the infinite sum. So let's go ahead and do that. So this is useful everywhere, actually. So if I have not this, but let's say I have some interest rate here, R, to the so I get, and let's start with I equals 0. So I get 1 plus R plus R squared plus R cubed. So somebody knows? So it looks, Mr. Gilstrom, it looks like this thing, but it might be a bit different. No idea. Well, first of all, if R is larger than 1, then equals infinity. You just have to do the partial sum. You get, imagine if R is 2, then it's 1 plus 2 plus 4 plus 8. So this goes to infinity. But if R is smaller than 1, so here is how you find it. So you write that the sum S equals to this. Then R times the sum equals to what? Equals to R plus R squared plus R cubed plus R fourth, and so on and so forth. And you see that here I have found almost the same thing. Here, this is the same term as this. R squared is here, R cube is this. So, and this difference is going to go on for forever, basically. So then what can I do? I can do S minus RS equals 1. See, S is 1 plus R, and RS is almost the same, but without the 1 there. So S minus RS equals 1. So S equals 1 for 1 minus R. And this, of course, as I said, is if R is smaller than 1. If R is equal to 1 or larger than 1, yeah, I should have. Yeah, greater or equal to 1. Then this goes to infinity. All right. So it's going quickly. I know it's a lot of useful stuff, but yeah, we have to move on if I want you to have seen enough stuff for the next TA session. But you know, if we haven't seen everything for the next TA session, it's at the end of the world, but it would be better. Okay, questions about this? No, all good? All right, linear models. So let me quickly justify this. So this is the most important chapter. So it's central to all areas of mathematics. So, yeah. So what can I do with it? Well, I can solve the same set of equations I had here, but in a systematic way. I can, so it's just describing the fact that having to solve a set of equations is so something that happens all the time in mathematics, that so we have to get yeah, tutorial 1 is uploaded on Moodle, yeah, and the solutions too. Yeah, that people have been trying for so long to find systematic ways of solving this kind of things. Yeah, record. Oh, a recording. Okay, I will ask her about this. She didn't have access to Moodle, but now she has, so she could put the recording online, probably. Yeah. Yeah. Okay. Let me ask her. Yeah. So basically, it allows to writing large systems of linear equations. Oops, sorry about that. In compact ways. And by large, I don't mean like 10 equations, I mean 10,000 equations. So if you have 10,000 equations, then you really need a good systematic way of writing it. And plus, you know, it's super difficult for your computer to solve it, so you need very good ways to solve it. So it allows to test for solutions. If you have one, infinite or no solutions, and provides many tools to solve systems that in a systematic way. So what about economics? Because in economics, you could have linear equations, but it would be very, very strange if the world always worked in linear ways. So we probably know that demand equations are not totally linear, that supply equations are not linear, so you can observe increasing marginal costs or decreasing marginal costs, who knows? And yet we still use all of these a lot. Why this is? It's because we never know what happens far from the equilibrium. So all we know is what happens close to the equilibrium, and for that, then a linear system is a good approximation. So let me just write this. So so I'll quickly share my screen so I'll tell you what I mean by this. Yeah, so imagine that I have a graph here. So I have my demand that looks like this, maybe. And oops, and I have my supply that looks like this. Who knows? Well, the thing is, I never observe this or this or this or this. It's like asking, oh, if the price, so the price is $10, what if the price was, I don't know, $50 or $100? What would be the quantity demanded? What could be the quantity supplied? Who knows? No economist will ever observe that because we have no way of testing it. So all we care about really is what happens very close to here. We want to compute elasticities. We want to say something like, no, you don't have to be in groups. You do it by yourself. Yeah. So all we care about is what happens here. So we care about this and this. So we care about what happens close to the equilibrium, and this is fine to be so we can imagine that this is linear. Who knows? We never have data about what happens here. So this is what I mean. So this is why we can use linear equations all the time. Okay. And we use Taylor approximation for nonlinearities. And this we'll see later. Okay. And lastly, if we really believe that a system, that a model is nonlinear, we can always transform it. So for instance, if I say y equals ax exponent b, then this is super nonlinear, but if b is not 1, of course, but what I could express is log y equals log a plus b log x. And this is linear. So we often do that in economics. So for instance, GDP, for instance, we don't really say, oh, what's the impact of, what's the impact of interest rate on the nominal value of the GDP? We say on the log GDP, or we compare log GDP with log population, for instance. So we use logs everywhere because it makes everything linear. All right, so now building blocks. So matrices and vector. So again, is this, so I guess some people, some among you are familiar with that. You can say it in the chat if you are. Yeah, okay, not a lot of people. Okay, so let's revisit the two market partial equilibrium. Yeah, so let me put this in. So what do we mean by this? All right, so I'm going to write it completely with just parameters. So, oops, C2 equals, I'm going to write minus C0. So this is just because I had C0 plus C1, P1 plus P2, C2, P2. And then I'm going to write gamma 1, P1 plus gamma 2, P2 minus gamma 0. So this is just a two equation system with two variables, P1 and P2. All right, and these are just parameters. This is gamma, it's a Greek letter, and this is C, this is a Latin letter. All right, so what we want to do is rewrite it this way. So what's wrong with this way of writing it? Well, it takes a lot of space. You see that P1 here is written in two places and P2 is written in two places. So we want to save ourselves some effort, and we want to consider this in a more structured way. So what we will say is, okay, we have stuff that are parameters that are multiplying our variables there, C1, C2, gamma 1, gamma 2. So these are on one side, and then we have our two variables. This is some other objects that we care about, and then we have our constant terms here. This is another object that we care about. So what we're going to do is rewriting it this way. So we're going to put our coefficients here: C1, C2. Gamma 1, gamma 2. And then we're going to have here our two variables, P1, P2. And here we're going to have our two constant terms, minus C1, minus C0, minus gamma 0. So, and then let me tell you what this all means. So, and this is another way of writing it this way. So AP equals C. A is a matrix, and it's C1, C2, gamma 1, gamma 2. It's a matrix of coefficients. P is a vector of variables, P1, P2, vector of prices. And C is C0, gamma 0. It's a vector of coefficients. So all right, A is this thing. We're going to see is a 2 by 2 matrix of coefficient. And P is P1, P2. A two-element vector of unknowns, variables we care about, that we would like to solve. And then C is, oh yeah, and there's going to be a lot of writing if you're writing all of this. Yeah, it's a lot of writing today. So a lot of definitions and stuff like that. Two-element vector of constants. Okay. So actually, I haven't said, oh, this is a matrix. This is a, so I want right away to show you what we use it for. So we almost always use them for this. So it's a simpler way, or it might not look simple to you because you're not familiar with it, but it's a systematic and compact way of writing a system of equations. That's what we use it for. So this is a matrix, this is a vector of 2 elements, and this is a vector of 2 elements. And I'm going to say even this is a column vector because we stack them together in column. And this is a column vector of 2 elements too. And you can, so we are going to say that a column vector is like a matrix of 2 elements by 1 element, because we have 2 elements, 2 rows and 1 column. Here we have 2 rows and 1 column. Here we have 2 rows and 2 columns. So this is a matrix of 2 by 2. It's like a matrix 1 by 2 and a matrix 2 by 1 and matrix 2 by 1. So that's one thing too. We always state the number of rows first and then the number of columns. All right. So in general, we write a system of n equations and unknown this way. So I can have A11 x1 plus A12 x2 2 A1n xn equals, let's say D1. This would be my first equation. And I could have 10,000 variables here, possibly, or more. Or I could just have 2, 3. And this would be my second equation. So I would have A2, 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 and AN, N, N, N. So where Aij is the height the coefficient. Of the ith equation of the jth variable. And we write it this way. So we would write A x equal D. And here A would be this very big matrix. So I would have A1, 2, A1n, then A21, A22, A2n, and AN1 here, AN2, ANN. What do I do here? Oops. X1, X2 to Xn, and equal to D1, D2 to Dn. Right. This is a very systematic way of writing it. So you see that in the end, I don't really need to know all the details here. I just know that all of this is in the matrix A. All of these variables are in X, and all of these constants are in D. And then all I can do is manipulate these objects here, and I know that the operations I do on each object is an operation that's happening on each each of these objects. So this is a very systematic way of writing it. And the matrix A can be compactly written A equals, we're just going to write AIJ. IJ equals 1, 2, n. So that's a neat way of writing a matrix, and this is going to be very useful for proofs. So questions so far? So I haven't shown you anything. I just told you how we write it. This is just been an exercise in writing down systems of equation. But please stop me if there's something unclear. Because otherwise I move on. If things are, if nobody is reacting, it's oftentimes because nobody understands or everybody understands. Okay, yes, Mr. Adams Gilstrom.
Yeah, I guess now we're just covering if you're adding a bunch of variables with the same power. But if you had to like a0 plus a1x plus a2x squared plus a3x cubed and so on.
Yeah,
We
so
could
then
still use this, right?
then that wouldn't be linear. So we wouldn't be doing linear algebra.
Yeah.
So and that would be much more complicated. But so what we tend to be doing is to solve the system linearly. So we say, okay, so let's see what's going on in some corner of the values we have, and then study what happens in other places. But yeah, so going higher or powers is, imagine you have like x2 and x3, and then you have y2, y3, z2, z3. It's just a mess. It's n-dimensional. It's but yeah, you can do that. Mathematicians do whatever they like. It's just yeah, it's much more advanced. Now we're just doing linear stuff. Okay, so general definition. So a scalar is some number. So it can be 1, it can be pi, it can be anything. It's just one single number. Then a column vector. Vector is a matrix with a single column. And then you might guess it, a row vector is a matrix with a single row. So a column vector would be this, for instance, and a row vector would be this, for instance. M by n matrix is an array. Oops. With m rows and n columns. We may write it A m times n. So this is a neat way of writing it. We say it's what the matrix is. It's called A, and then we tell it what dimensions they are. Or sometimes people write it this way, but here I think we are just going to write it without. So, as everywhere in mathematics, there are popular ways of expressing stuff, but they don't have to be. It's like in economics too. Sometimes you see some type of notation, sometimes you see some other type of notation. And a square matrix has the same number of rows, columns. So like this, for instance, here we have n rows and n columns. Some notes. So sometimes you will see this. So sometimes you see parentheses instead of square bracket, but to avoid confusion. All right. It's a notation thing again, but sometimes you may say you may see a parentheses instead of brackets, but we'll always use brackets. Yeah, many notations. All right. So I would say let us do a bunch of operations, and then we can take the break. So equal matrices. Oh yeah, and by the way, somebody knows how you call a matrix with more than 2 dimensions. So m by n by p, for instance, which would be a cube of numbers instead of a square of numbers. No, nobody knows. So I'm not going to write it because it's not useful for us, but it's called a tensor. So a tensor is a 3, 4, or 5 dimensional matrix. If you do programming, then you use tensors all the time. All right, equal matrices. So A is equal to B if Aij equals Bij. Oh yeah, and by the way, so that's something else too. Sometimes you see this. This is a bit more precise, because if I write so A1, 2, then I know that it's row 1 and column 2. But if I write A1, 2 this way, then it looks like if it's 12. So it's a conundrum whether you should write with commas or not. Here I'm writing them without commas when it's obvious, but know that we could write them with commas just to make sure. Okay, so two matrices are the same if all of their numbers are the same. So if I have a matrix with 1, 2, 3, 4, then it's going to be equal to another matrix if the other matrix has 1, 2, 3, 4, 2. All right. Transpose a matrix. You invert columns and rows. So would write A prime. Sometimes you also see A T for transpose. In mathematics articles, if you take a math class, it's oftentimes you see AT for A transpose. So, but in economics, people usually use A prime. So I'll stick with A prime. So equals Aij prime. So it becomes A Ji. So you invert the rows and the columns. So let me show you an example. So if I have 3 by 2, where I have A1, A2, P1, P2, C1, C2. If I take the transpose of this, then I get so first of all, I had 3 rows and 2 columns. Now I have 3 columns and 2 rows. And of course, so A1 is still at the same place. P2 is still at the same place, but then A2 becomes here, B1 becomes here, C1 becomes here, and C2 becomes here. This is how you find the... So just to see if you're following. So what is A prime prime?
A prime.
Yes, exactly. No, not A prime, A. Because if I take this transpose, for instance, this transpose, I get exactly this one. A is B, and then AB, A1, B1, C1 is here, A2, B2, C2 is there. So A transpose equals A. All right, note, by convention, vectors are column vectors. So usually what this means is we care more about columns first than rows first. But this really is a convention. We just decided that this would be the case, but it doesn't have to necessarily. So what I mean by that is we would write something like v, a vector v, would be equal to v1, v2, and v3. And the transpose row vector is denoted v prime equals what dimensions? One by three, yes. So I get v1. Oh yes. v1, v2, v3. Yeah, or sometimes you just write, if you write it in the text, you will write v prime equals v1, v2. So if it's like inside a text in a scientific article, then that's oh, and then yeah, exactly. It's the way you would write it, and then people understand that the real vector is this thing, but transposed, so vertical, so like this. But I don't want to confuse you. I'm never going to write this. I'm just telling you this is sometimes what you will see. Yeah, lots of notation there. Okay, so it's 10:03. So how about we take 10 minutes and then we come back for much more. All right, so back in 10. Okay, Patrick, I don't know if you're back. So question is, aren't there not vector, but matrices that can't be transposed? Or is that their inverse? Yeah, so no, all matrices or vectors can be transposed. Yeah, I don't know if there's a proof of that, but it seems quite obvious. If you can write it in one way, you can write it in another way. So if you look at this way, you just take the mirror image. So you have this, the symmetry can be done for any matrix. But it's absolutely true that when it comes to inverse, then it's really not all matrices have inverse. So we'll see that later.
Yeah, no, I guess the word that comes from is when I did linear in college, it was like you had certain matrices where you couldn't switch IJ to JI because of the way the matrix was set up, or it wasn't m by n matrix, it was m by n.
No, you can always, from what I can tell, I think you always have a transpose. But inverse, that's true. If inverse, first of all, you need a square matrix to inverse a matrix. So
Right.
we'll get to
So
inverses.
it's inverse.
Yeah,
Okay.
yeah, inverse. But you're totally right. Inverses, you have many different conditions. Yeah, exactly. Okay, so we've done. What have we done? Yeah. Oh yeah. Okay. So multiplication by a vector, by a scalar. Sorry. So if I have S that multiplies a matrix A, then it's equal to S that multiplies each element of the matrix A. And it's equal to each element multiplied by the matrix, each element of the matrix A multiplied by S. So that's pretty obvious. So for instance, so if I have this, for instance, or this, S times this equals to, let me be, oh no, I think I don't even have to do that. Let me try something. Yes, it gives it to me. It's a nice program to have. All right. Addition of two matrices. So if I have a matrix A, that's M by N, and a matrix B, that's N by N, then each element are added together. So I get Aij plus, so that's another way of writing the same matrix A, plus Bij equals, so each element are added in pairs. So for instance, if I have, So let's take this matrix there, plus some other matrix, C1, C2, D1, D2 equals to this. A1 plus C1, A2 plus C2, B1 plus D1, and B2 plus D2. Note, very important, both matrices need to have the same dimensions. Otherwise, it doesn't work. So I have a 3x2 plus a 2x2. It doesn't give you anything. You cannot do the plus operation. All right. So what you're going to see is that all the operations you know, so addition, multiplying by a scalar, so they have somehow their equivalent in matrix form, but different. So somehow, so you have to adapt them in some way. So you have to, you can use your intuition, and sometimes it's going to work. So you think, oh yeah, I can add two matrices. It's probably going to give me something like this. But you have to be careful. Matrices are more complicated. You have to check for conditions each time. So here the conditions is, if it's a 2x2, then you can just add it with another 2x2 matrix, or n by n, you add another n by n matrix with it. All right, so these were the easy things. Now let's go for the less easy things. So vectors or products. So I'm not going to do, so I don't know how, so people who have seen matrices, oh yeah, okay, so extremely good question. Does division have a matrix equivalent? No. So you don't have no division equivalent. But you have multiplication by inverse. So this will be our division. It's multiplying by the inverse of a matrix. And if you have scalars, then you can say that x divided by y is equal to x multiplied by 1 over y. Or it's equal to x multiplied by y minus 1. And we don't have x divided by y for matrices, but we do have a notion of inverse. And that's what we're going to see. And of course, this is going to be a fundamental thing in linear algebra. All right, so as I was saying, I don't know how you learned things, but so I really thought about it. How should I explain to you in the most intuitive way? I think the best way is to start with vector products. And once we have seen vector products, then we can go to matrix products. All right. So which are just vector products, because vectors are just special matrices. So in the end, it's all going to be the same, but it's just good to start to go progressively. So consider two vectors. So imagine I have V, which is V1, V2, and V3. And I have W, which is W1, W2, W3. So I have two vectors. So you are going to see two types of vector multiplication. First example is inner product. Inner product, which is written V prime W. And what is it? It's so V prime, so V prime is the transpose of V. So I get this V1, oh, sorry. V1, V2, V3, which multiplies W1, W2, W3. And what do I get? I get the sum of each element by element multiplication. So I multiply the first element of V with the first element of W plus the second element of V times the second element of W plus the third element of V times the third element of W. So I get essentially a one by one matrix. But when we have a one by one matrix, usually we don't really care about the fact that it's a matrix because you couldn't divide by a one by one matrix, for instance. But if it's a scalar, then you can multiply or divide by it. So all we're going to say is, yeah, so it would be something like this. So V1, W1 plus V2, W2 plus V3, W3. And so we don't really care about the fact that it's a matrix. So this is something that it's much more relevant for computer science. So it's a big debate, but so for now, let's keep it simple. If it's a one by one, we can imagine that we can get rid of the fact that it's a matrix. And why did I show you sums? Well, because they are super helpful for matrices. So it's the sum for I equals 1 to 3 of what? Somebody has an idea?
It would be the sum of VI times the sum of the same thing, but WI.
Are you sure? So this would be V1 plus V2 plus V3 times. Yeah, exactly. So it's.
No, I'm wrong. Yeah, sorry.
It's VIWI. It's a less term. So yeah, if we did what you suggested, it would be more terms. Yeah, exactly. Yes. So next, so there's a question. Is there a V prime plus W? So this no, because they wouldn't be. I think you meant multiplied. Is there a possibility of having V prime multiplied by W? Was that the question? Oh, plus, well, plus no, because I would have a 3 by 1. Sorry, V prime times V prime plus W. I would have 3 by 1 plus 1 by 3. So does it work? No, because I have to have the same dimensions on both of them. So no, it doesn't work. All right. So that's the inner product. And now if there's and of course, one condition again, both vectors need to be the same length. So what would we use this for? Well, I could give you an economic example. So total spending on two goods. With prices P1, P2, and quantities Q1, Q2. So how would I do that? Well, I just have P equals P1, P2, and Q equals Q1, Q2. And what do I get? So total spending is what is it?
Would it be PQ1 plus P2 times Q2?
Yes, exactly. So how would I write it in terms of inner product?
The same as V1, W1.
Yeah, but so what's my expression? It's this, right? So it would be P prime Q. So that's the neat thing about algebra is here, I don't have to know exactly how many goods I have. I just say I have my prices in this vector P and my quantities in this vector Q. And here I get total spending. That's it. Equals to this, yeah, P1, Q1. But you were totally right, of course. P2, Q2. Yeah, question?
Yeah, I lost you on why we put the notation P prime.
Oh yeah, so well, that's the way we write it. So
okay, it doesn't have the meaning of because we're not technically inversing it, no?
Yeah, no, but you are taking the transpose. So V prime is the transpose of V. So you have V is V1, V2, V3. So when you do the inner product, you do the transpose V1 plus V2 plus V3 here this way, 1 by 3, multiplied by this. And that's going to be a general rule for multiplication is to multiply two things, like two vectors. It has to be the case that the number of columns of the first vector equals the number of rows of the second vector. So, okay, maybe it's, so I'm doing it this way because you see that inner product is one thing, but you also see that this mechanism of multiplication is something that you're going to see everywhere in matrix multiplications. Just wait 5-10 minutes and you're going to see it. Yeah, there was a question. So if you ask V times W with this example, the correct response would be, so there is no answer exactly, perfectly. Well, yeah, so VW, yeah, exactly. So VW doesn't exist. What you could say is, so again, we're doing math, but if you're doing computer science and so you're programming something and you have one vector here and you have one vector there, and what you would like to have is a vector with V1 times W1 and then V2 times W2 and then V3 times W3. So of course you can you can ask your computer to compute this for you. So I'm not saying this is impossible. It's possible. It's just not how we define multiplication in linear algebra. And you're going to see why this makes sense later on to multiply this way. Well, so basically, this is my explanation for why it makes sense, because we want to do something like this. So we want to have something like total spending. So if I want total spending, then I can just multiply. So if I want total spending on one good, I say it's P1, Q1. So that's total spending on one good. Then total spending on all goods is P prime Q. So that's one way to do it. Yeah, and now we're going to see another type of multiplication. So is that good for the inner product? I know it's shocking at first to see, oh, it sounds arbitrary. Why can't I, why isn't it defined in some other way? Well, it's a useful way to define it this way. Let me just put it this way. Okay, so second sort of product, the outer product. So if we have an inner product, we have an outer product. Yes, so Mr. Deng, if we write P Q prime, then we don't have an inner product, we have an outer product. So it's somehow like the Cartesian product. So if you remember the Cartesian product, if I had one set with X and Y and the second set with 1, 2, 3, then the Cartesian product was associating each element of the first set with each element of the second set. And you got like a big bag of all the possible combinations. So outer product looks the same. So going back to my example, so V and W. So if I have V W prime, this is the outer product. And how do I write it? I write it this way. So V. So now V is in its first, in its original way, it's just a column vector. But now I multiply it with W prime, which is now not a column vector, but a row vector, or a 1 by 3 matrix. So W1, W2, W3. And here, what do I get? I get not a number, but a matrix, a 3 by 3 matrix with all the possible combinations of both. So for the first corner element, I get the first element in the first row of V and multiplied by the first element of the first column of W prime. So I get V1, W1. Here I get V2, W1, V3, W1. And here is the same with W2 and W3. So that's completely different. It may look strange, but it's that's the way you do it. And if you think about it, it's coherent with the last thing we've said. So the last thing we've said is here I multiply all the elements of the first row with all the elements of the second of the first column, and I do the sum. Well, here my first row has a single element, V1, and I multiply it with all the elements of the first column, which has a single element, it's W1. So their sum is this, V1, W1. And I do the same for the second one, V1, W2, V1, W3, and blah, blah. So here it looks like I'm taking all the combinations of all the possible way I have to combine. I can combine them. And question, do I have restrictions about dimensions here? Do you think? Yes. Well, here it is. It's the case that the rows equals a column, but I could not have that. I could have, this would be perfectly fine. So no restriction. Oh, yeah. No, actually, there is one restriction. So it's vectors. So vectors, they have a single column or a single row. But it's true that there has to be that it's a vector. So the first vector has a single column and the second vector has a single row. So I can do element by element. Otherwise, yeah. So for vector, no specific restriction. So I can give you some example again. So imagine that I spend spending on one good. So here I had two different goods. Here I'm just going to have one good, but the price changes with the day of the week. So let's say I have Monday price, Wednesday price. I'm not going to put 7 because it's long. And Friday price. Let's say I just go to the market 3 times. And now let's say that the quantity but changes with seasons. So I have something like summer S, winter W. And now what I can have is so I can write it this way. So vector of price would be equal to, so PM for Monday, PW for Wednesday, and PF for Friday. And I can have the vector of quantities, which would be 2 sort of quantities, so either summer or winter. So QS or QW. And then the outer product would be a 3x2 matrix of all possible spending combinations. So I would have something like PQ prime, which would be equal to And then I can, here I have all my QS and all my QW. So you see that it's a completely different concept. So now I would have a quiz on all of this, but yeah, we still have more stuff to see. So. Questions about this? I know it's going fast, but yeah.
So sorry, just so I understand. Hopefully I say this clearly. So in the first instance, the inner product would be used when the variable inside each of the vectors, there's only one variable. Basically, it only changes. There's only a possibility of it changing between like P1 and P2 only once. But then we use the outer product when there's a possibility of multiple changes within that vector.
Yeah, in a way, but you can have like 3 goods, for instance. So I could have P1, P2, P3, Q1, Q2, Q3. It would just be a sum of more elements.
Yeah, I'm just trying to understand like in what examples we would use either or. So I would use the inner product.
Inner product if you want if you want them combined and sum, and the outer product if you want all the possible combination of each element.
Okay.
And then, but then I can show you that actually matrix multiplication is both of them. So let us just finish with this. So matrix multiplication. So matrix multiplication is just inner product for every possible element of the outer product. So yeah. So to multiply two matrices, A and B. So you do A times B. So you have A that's M N, and B is N times P. And what you get is a matrix C that is M times P. All right. And the condition is columns of matrix A have to equal rows of matrix B. So you see that the columns of matrix A is n. I have n columns, and this has to be equal to the rows of matrix B. And this is what this is our condition for the inner product. Columns of matrix A would be here 3, would be equal to the rows of matrix B, which here would be 3. That's the only way you can add them all together. Combine them together. All right. So each element ij of the resulting matrix C is the inner product of the row I of matrix A with column J of matrix B. So C would be equal to, yeah, that would be complicated to write down. So let me just write a resulting matrix. Has same rows as A, same column as B. Yeah, so I don't know if I should write this down. It's quite long to write down, but I'll just go to the example quickly. So let's start with the inner product that we've seen before. So example. Total spending on Monday in the summer. So I get PM1 on good one. PM1 PM2 oh no, sorry, yeah, on all good, on both goods. Total spending, yeah. Q1 PM2 times Q1 S Q2S. So that would be equal to, I can just compute them here. So that's, as we've seen, that's an inner product. So P1, PM1, PM2 times Q1S, Q2S, that would just be the sum of P1, PM1, PQ1 plus PM2, PQ2. So it's exactly, I've just done exactly the same here. It's just I've said that it's on Monday in the summer, all right? So imagine that we do this inner product, but on Monday in the summer. So that's why I added this M to say that it's Monday prices and S to say that it's summer prices. But then what I can do is say, oh, actually, I'm interested in not only on Monday, but every day of the week. So what I can do is total spending any day. In the summer. And what I can do is just stack these prices below the first row. So I would just get P1M, P2M, PM1, PM2, and then Wednesday, and then Friday. So Wednesday and Friday. Wednesday for good 2 and Friday for good 2. And just like that, I'm able to find the answer. And I get the inner products. So so I just follow my definition. So each ij element of the resulting matrix is the inner product of the first row of matrix A. So here it would be PM1, PM2 multiplied by the jth column of matrix B. So here I just only have one. So PM1, PM2 multiplied by Q1S, Q2S. So that's my first spending. So here I get spending on any day in the summer because I only have summer quantities. But I have two goods. And then lastly, what I can do is total spending any day, any season. What do? I just add my winter quantities. So Q1S, Q2S, Q1W, Q2W. And I get this matrix there. So this is how you do matrix multiplication. So here I get a 3x2 matrix multiplied by a 2x2. So I get a 3x2 result. Okay, so now I'm guessing I lost most of you, or you have been writing a lot. Any questions so far, or are you just writing down everything? I'm going very fast. That's because you have a lot of things to see for the TA session. But since we don't have, we haven't seen everything we needed to see for TA session 2, then you do what you can, and next week we continue. So do someone want me to stop and ask a question, or I can give you maybe a few examples just to see if you understand? A few examples. Now I'm going to wait for you to answer. So if nobody answers, then I know that you're lost. So if I have 2, 3, B equals to yeah, there's no Cartesian. So this looked like the Cartesian product, because the Cartesian product, what do? We pair each of element of set of the first set with each element of the second set. So this is sort of what we're doing, but then we're multiplying them. So V1 W1, then V1 W2, V1 W3, V2 W1, V2 W2, V2 W3, V3 W1, V3 W2, V3 W3. So that's why I wrote somehow like the Cartesian product. Okay, so B, I'm got A, B, C, D, and C I have so gamma and pi. So what is AB? Okay, now somebody has to tell me, otherwise I know you're lost. Somebody knows?
Would it be 2A plus 2B on the first row? And then below 3C plus 3D?
I think you're muted.
Professor, you're muted.
Yeah. So first question is, can I multiply A and B? So what is the condition? Sorry. Yeah, so the columns of A, I have A has 2 columns. This has to match 2 rows of B. So these match. 1 by 2 times 2 by 2 works. And then I do the inner product for the first row. It's going to be 2 times A plus 3 times C. And the second, it's going to be 2 times B plus 3 times D. All right, and I only had one row on A, so that's it. That's the only thing I get. And I see we're out of time. I had so many other things I needed to show you. Let me think. Yeah. All right. Oh, it ends at 11:30. Is that so? Oh, okay. Okay. I'm so happy. I thought, wow, it went by too fast. Okay, let me grab my water, and then I can ask you. Think about this one then. BC. Can we do it or not? What are the dimensions? I'm just going to grab my water. No. So so what did I write as condition? Condition, columns of A have to equal the rows of matrix B for the product to exist. First condition. Columns of A, I have 2 columns. Columns of B, I have 2 columns. Rows of C, I have 2 rows. So 2 columns, 2 rows. So that's possible. Yes, you got it perfectly right, Patrick. So what are the dimensions of the resulting matrix? Let me ask a random victim. Let's say Eddie Nedi. Eddy. So what are the dimensions of the resulting matrix P times C? Eddy is not with us. Okay, somebody wants to help your colleague. 2 times 1. Yes, so the resulting matrix will have the number of rows of the first, so it's 2 rows, and the number of columns of the second one, so 1 row. And yeah, Patrick said it perfectly, so I do the same, so I get A times gamma plus B times pi. And then the second element, the second row is C times gamma. Plus D times pi. Yeah, this is, it's probably looking very strange to you. It's just, I can tell you, there's one way for it to not be strange, is to practice all the time. So do a lot of matrix multiplications at home, try a lot of things until you get very good at it. It's something that you have to become, you have to just practice to be good. All right, next matrix, AC. Can I do it? Yes, because it's exactly as if A was 2, 3, and I was doing the inner product. Here it's already transposed in some ways. So I get 2 times gamma plus 3 times pi. All right. Next one, CA. Can I do it? Yes, it's like an outer product. So here I have, I can check, I have 1 column for C and 1 row for A. So 1, 1, I can do it. How many rows do I get? I get 2 rows. And how many columns? 2 columns. So I get that 2 by 2. And I just combine them together. So I get 2 gamma. Here I get 3 gamma. Here I get 2 pi. Here I get 3 pi. Okay, so yeah, I had a quiz on this to help you learn it. Sadly, we don't have time, so we have to move on. That's the way the class works. It has to go very fast. Otherwise, you don't have enough material for the TA session, the next TA session. AC part, I multiply 2 gamma. Oh, yeah, sorry, I made a mistake. 3 pi. Good, thank you. Yeah. So you really see that matrix multiplication is really just combination of inner product and outer product. So I started with one and then the other just to really show you the 2 things that are going on is we're combining columns and rows in specific ways. And if you have vectors, you can combine them this way to get just a number, or you can combine them this way to get this whole matrix there. And then this is just to show you how you would go from inner product, but then if you consider different days of the week, then you just tag this result on top of the other. And then if you consider different season, then you just put them here. So and then you get all these matrices. So maybe that's helpful, maybe that's not helpful. That's how I thought I would make it sound useful for you. So who knows? But yeah, it's, you know, as long as you understand the mechanics of how you multiply them, that's good. Okay, so properties of matrix algebra. So, and of course, it would be much easier for you to understand all these properties if you're familiar with addition and multiplication. So, but yeah, so yeah, we're going fast. So follow as best as you can, and you can go back on the material if you're not sure. So properties of additions. Oops. So A plus B, is it equal to, oops, B plus A? What do you think? You can venture a guess. Yes. Of addition. And let me, so this is, yes, equal. So how do we show this? Well, we just use the commutativity of scalar addition. So if I have Aij, so I'm just going to use commas there to make sure. Oh, no commas. Plus Bij, it's equal to, of course, as we've seen, Aij plus Bij, and that's equal to Bij plus Aij, which is equal to Bij plus Aij. And here, what did I use? I used the commutativity of addition. So do I want to show you this to torment you? Not really, but no, I don't. I'm not tormenting you, but I want to show you how you think about proving things. So because you're going to have to prove a few things here and there, but not difficult. It would be a shame to have a math class with zero proof in it. But yeah, know that I'm not going to ask you very difficult proofs. Okay, so associativity of addition. So A plus B plus C equal or not equal A plus B plus C. Yes, equal. Or maybe that was an answer to the previous one. And the proof is exactly the same. So that's what you write when you're not too sure. So do the same thing, and then you can see that it's possible to use associativity of addition to prove of scalar, to prove the associativity of addition of matrices. Now, commutativity of, yeah, so now it's properties of multiplication. A, B. Okay. Yes, no, maybe.
No.
Good. So no. So to prove a negative, it's much easier. All you have to give is a counterexample. So counterexample. So if you can find one way in which it doesn't work, then it means that this property is not valid. So of course, we know that we've seen that if it's if you start with a 3x1 and 3x1 or 1x3, you get a 3x3, and if you invert them, then you get a 1x1. So you know it doesn't work. But even for when the matrices have the same dimensions, so I can show you, for instance, A, B, C, D, E, F, G, H. So it gives me this. And if I invert them, so this times this gives me something different. So AE is still there, but then the second element here is BG, and the second element here is CF. So already we know that it doesn't work. So so multiplication is not commutative. Distributive law. So if I have A that's m times n, that multiplies P that's n by P. Plus C that's n by P. Is it equal to, like for scalars, AB plus AC? Yes. All right, so maybe I can give you a proof for that. So it's like the distributive law for addition and multiplication. So I get A times BC equals A times, then B plus C is the matrix B JK plus C JK. So where j equals 1 to n, and k equals 1 to p. So you have to keep track of dimensions, that's for sure. And now I can use this, I can then multiply each individually. So if I do the multiplication, I get that this is equal to sum. So this is each element of Aij times Bjk plus Cjk. This is the inner product for every element of the matrix, where I equals 1m. And this is equal. Now what I can do is use the distributive addition. So it's equal to this plus this. So this is equal to, so this is just, I can just say that this is an addition of two matrices. And it's, of course, equal to AB plus AC. Yeah, sorry if this is going very quickly. I don't expect you to follow along each step of the proof, but this is how you demonstrate things in general for matrices. And here the product of two matrices, it's a product of Aij. Oh yeah, and I didn't write, sorry, I didn't write. This is of course from J equals 1 to n. Yeah. One very tricky one. I had prepared a proof for you, but it's just, it's really, really complicated to understand, so I'm not going to show it to you. Associative law of matrix multiplication. So if I have AB times C, which would be P times Q, for instance. Then this will be equal to, I'm just going to write it already, so A times BC. Believe it or not, you can show it in like 5 lines that this is true. It's just messy to think about it. So if you want to try, it's yeah. No, don't try it. You're going to try it for 2x2s. To see it works. And now, of course, what you need to have is m times n times n times p times P times Q. Yes, yes, of course, yes. Now we're going along. Property of transpose. A plus B transpose equals to somebody has an idea? Yes, A transpose plus B transpose. And AB transpose equal to, somebody has an idea? Almost. Almost. Combine the two answers. Mr. Jacobi and Sheikh Miri. Yes, B transpose, A transpose. So just to show you how this is the case. So if you have, for instance, A is 3 by 2 and B is 2 by 3. So if you transpose it, so you get 2 by 3 by 3 by 2. So the only way to make sure that the multiplication still works and the dimensions are maintained is to invert them. Yeah. So again, I'm not going to show the proof of that. It's very, very messy. Even I had a hard time wrapping my head around it. All right. Special matrices. Okay, I'm just going to show you one, and then we can continue this later. So idempotent matrix. Idempotent. I have doubt. Is it idem or idempotent? Yeah, idempotent. So it's AA equals A. So for example, if I have a matrix that's 4 minus 1, 12 minus 3. So times the same thing, it equals to 4 minus 1, 12 minus 3. That's very strange, very weird. But if you look like it, for instance, 4 times 4 is 16, and minus 1 times 12 is minus 12. 16 minus 12 is 4. Do that for all the elements, and you see that you get exactly the same thing. Yes, so yeah, A equals I works too. Yeah, I can show. Yeah, we only have 3 minutes. So let me show you one concept before we leave so that you can do this exercise in the TE session. So concept of linear independent vectors set of vectors v1 vn is said to be linearly independent if and only if. So if I write this IFF means if and only if. So it means that if x y, it means that if x is true, y is true, and if y is true, then x is true. So that the if works in both ways. One of them can be expressed as a linear combination of the others. So for instance, if you have v1 equals one, 2, and v2 equals 2, 4, then you can say that v1 equals 2v2, v2, sorry, equals 2v1. So they are linearly. Oh, linearly dependent, sorry. All right, dependent. And it works too if you have v1, v2, v3, for instance. So v3 is linearly dependent of v1 and v2 if there exists A and B such that v3 equals A v1 plus B v2. Yeah. All right, so that's the last notion that I wanted to give you today. I think you can do most of the TA session with that. And next class, we're going to go back over many of these concepts and add more special matrices and continue there. I'm sorry it went so fast. I would have liked to give you more proofs, let you do exercises, but yeah, the class has to move along quite quickly, I realized. So question before you leave?
Are we going to need to know these proofs?
Yeah, so for proofs, so you have to make, sorry, I'm here. You have to, you're going to be asked to do some proofs at some point. So when you do, but they're not difficult, but it's just to train you a bit to think logically and to try your best. Okay, I can do that. Yes, I can post the notes. And then what you can do is say, oh, as I did here. So for instance, here I say, okay, proof that this is true. So A plus B is AIJ plus BIJ. This is the definition of addition of two matrices. So I could even add addition of two matrices. And then you say, okay, this I can revert these. And then you say, why are you allowed to do that? Okay, because I have learned that there is this rule, commutativity of addition, which allows me to say that A plus B equals B plus A. So each step, try to justify your step, why you're doing it, and then you can reach this. Then if you need, for one of your step, you need one thing that we just saw in the class, then you can say, okay, I learned that addition of matrices is commutative. So I can use this in my own proof when I do it. So I can, if I want to prove something, at some point I need to invert two matrices, I can write commutativity of matrix addition, for instance. You're not graded on the TA sessions, of course, the exercises. The goal is to train you, but yes, you're going to have to make some simple proofs. Okay, so yeah, you just have a few moments to get ready for your for the next for the TA session, actually. Yeah, okay, so I'll ask her to upload the recordings. All right, so well, thanks a lot, and yeah, I see you next week.
Thank you.